today we're going to look at the math features of Deforum stable diffusion, which allow us to create motion in the translation and other parameters in the animation settings. Unlike angle and zoom, which proceed with each frame at a steady rate. For instance, if we put in zoom 1.02, that's a 2% zoom in every frame for the duration of the video. Similarly, if we put in an angle of 1, that's a 1 degree rotation, clockwise rotation, each frame, and it just keeps rotating or keeps zooming. However, if we want to do that with, for instance, the translation parameters, we have the variable t, and t allows us to use the frame number in order to animate the parameter. So in this case, the image is going to move down by 1 unit each frame because t is the frame number. So in the first frame, the y translation will be 1. On the second frame, the y translation will be 2. On the third frame, the y translation will be 3, and the image will be pushed down the screen. Now the problem with this is it's just going to keep going. It's going to get pushed off of the screen and it's not going to come back. So take a look at that. I just ran that. And there's our y translation going down, and it's just going to keep going down, and there's no way to get it. I mean, that's the video looping there, but there's no way to get it to return, to dip down and then come back up, just using the t parameter. And we can slow the process by doing some simple math on t. For instance, we can just say t divided by 10, and it's gonna drop down at 1/10 the speed, but the problem remains the same. It's still gonna keep going in the same direction. It's a linear progression. So that's what this expression that we looked at previously is about. 10 times sine 2 pi times the frame number divided by 10. That is, if you look at the video again, you'll see that there's a back and forth motion. It's moving back and forth on the x-axis. Left, right, left, right, left, right, left, right. That's what that expression is doing. It's moving the camera back and forth, moving it on the x-axis according to this expression here. So why is this expression so much more complicated? Well, because it is turning the linear parameter of t, which just keeps counting up with each frame number, into a cyclic parameter, where it goes one direction, then reverses and goes the other direction, then reverses and goes the other direction. So just to illustrate this, so here's our frame number, t. At frame 1, it's 1. At frame 2, it's 2. At frame 10, it's 10. At frame 20, it's 20, etc., etc., etc. And if we divide it by 10, it changes the slope. It increases more gradually, so that at frame 100, it's at 10. But still, it keeps going up. So we have two ways in math, easy ways, of turning a linear value into a cyclical value. And the first is the trigonometric functions, of which we're going to talk about two today, sine and cosine. And sine takes an increasing value like t and causes it to oscillate from 1 to -1. I'm multiplying it here by 10, so it's going from 10 to -10. I'll take that out and just zoom in on this, and we'll see that as t increases, the sine of t increases to 1, then drops back down through 0, goes to -1, comes back up to 0. So it's taking the linear progression of t and turning it into a cyclic progression. The other one is modulo. And modulo is just the remainder of a division. So at frame 10, we'd say 10 divided by 10 is 1 with a remainder of 0. So at frame 10, this value drops back down to 0. At frame 11, it's 11 divided by 10 is 1 with a remainder of 1. So our value becomes 1. At 12, it's 12 divided by 10, which is 1 with a remainder of 2. So the remainder follows this sawtooth pattern. It increases and then drops back down to 0. So these two mathematical functions we can use in the notebook in order to produce different repeating patterns. So let's take a look at the example that's the default when you open up a new copy of the Deforum Stable Diffusion notebook. It's 10 times the sine of 2 pi times the frame number divided by 10. That's hard to wrap your head around. So we can take a look at the basic principles that are behind this to understand it better and build our own expressions. And one of the ways to do this requires just a little bit of programming, but a little bit of programming is going to allow us to visualize how these different formulas work so that we can apply them in our animations. So let's make a new notebook and save this as command line. And we're going to come back to this command line notebook. There's a lot of stuff we can do in here because this is part of the nice thing about working in Google Colab is it's also a programming environment. So we're going to install a couple of packages that are going to help us out here that you may already have them installed. Pip install numexpr and numexpr. Numexpr is the math package that the notebook actually uses. So by having this installed, we can enter our expressions in exactly the same way we're going to enter them into the notebook, test them, and make sure that our formatting is correct on the messages and that they make sense, and also see what they do. So this is already installed. I'm going to add a new code block and do a pip install numpy, numpy, and numpy is a more common math extension for Python that we're going to use just in one of the lines of the code that we're going to make in class. And then also, just so we can see our results, we're going to install a graphing package, pip install matplotlib. And that'll install. And that stuff is all installed, so that's great. Let's make a new code block, and we'll import these. Import numexpr as any. So we're just making abbreviations for these. Import numpy as np, and import matplotlib.pyplot as plt. So now we have those three abbreviations. And the only thing we're going to use numpy for is just to put a bunch of frame numbers into an array. So we're going to make an array for t, which is our frame numbers, and we'll do numpy np dot arange. And this is not arrange with two r's, this is arange. and we're going to just put in frame numbers 1 through 50. And I'm going to write an expression. So I'll call the expression E. I'll call it E1 since we're going to do multiple expressions. And I'm going to do NE evaluate, and then some expression that we would type in here. I'll just copy the default expression here. Copy that and paste it in here. And I'm going to add some spaces after my expression just to make it clear where it ends. It's going to want to put a period in there. I'm going to delete that period. So just check that I've got this. E1 equals NE evaluate, and then the expression I want to evaluate in quotation marks, close the parentheses, okay? And then I want to see the result. So I'll say for I comma v in np.nd enumerate E1 colon, and I'm going to print T bracket I close bracket comma F quotation mark curly bracket V colon space dot 2F close curly bracket close quotes close parentheses, and let's see if that runs, and indeed it does. So now it shows us what the value is going to be. In this case, we're using this to get the X translation value, what the value is going to be at every frame. So at frame 1, the value is 5.88. At frame 2, the value is 9.51. At frame 3, the value is 9.51, etc., etc., etc. And we can see it goes positive, then it passes through 0, then it goes negative, passes through 0 at frame 10, goes positive again, comes back, passes through 0 at 15, and this represents the values that are being sent to the X position of the virtual camera here to move the image back and forth. Now, of course, looking at this column of numbers is not that great, so that's why we installed pyplot. We'll just comment these lines out, and we'll do the same thing, but graphically in pyplot. So we'll say plt figure fig size equals parentheses 10 by 3 inches. So 10 by 3 graph of these numbers. And then we will plt dot y label will be parameters, plt dot x label will be frame number. Put the grid on, plt grid visible equals true, and then we'll plot the values. Plt plot T against E1, and let's see if that runs. Yes, and there's our plot. So this is the frame numbers along the bottom, and these are the values. So we can see it's going at frame 1, it's starting just above 5, rising up to 10, dropping back down to negative 10, and then passing through 0 again at frame 10. And it repeats that pattern, and that's the motion that we saw in the video. And just to help visualize this a little bit, I'm just going to put a heavier line at 0. I'll do plt plot t minus 1 t times 0 that should, yeah, just give us a heavier line at 0, starting at frame 0. There is no frame 0, and we can see our chart here actually starts at frame 1. So this is great. This is going to allow us to visualize our expressions exactly as we type them into the notebook. But let's first look at why this is the result of this expression. So let's ignore the 10 times here for a minute. We'll think about that last. So we're looking at the sine of 2 pi times t divided by 10. So let's just look at the sine of t for a moment. So the sine of t is going to go from a 0 point to a 0 point every pi frames, every 3.14 frames. And that's just not a very useful number to think about. And it's going to go down and up and return to 0 every 2 pi frames. And again, hard to think about. So that's why we just multiply t by 2 pi. .28 times is the asterisk, 6.28 times t, and now we're going to get, let's look at this over more frames. Look at it over 2,000 frames. So now I'm getting my entire movement here over 2,000 frames, which is a much nicer number to deal with, because if I want it to be over 100 frames, I just divide by 100, t divided by 100, and now it's going to oscillate every 100 frames, starting at 0, going up, crossing down through 0, landing back at 0 at frame 100. So now we're starting to understand the logic of how the math in the Stable Diffusion notebook works. 2 pi times t divided by 10 times 10. So the reason for the times 10 is because this is oscillating from 0 up to 1, back down through 0 to -1. And this would create very little variation in the image. A value of 1 here is not going to be very much displacement of the image. So let's take a look at the difference. We'll put another expression in here. I'm going to copy this expression and paste it on a new line, call it E2. Can add some spaces here for readability. Any evaluate, and I'm going to say 2 times the same thing. And I'm going to plot that as well. So I'm going to plot E1 and E2 and run this again, and now I can see, aha, my new one in green here is taller. It peaks at 2. So in the Stable Diffusion notebook, the default is actually 10 times sine 6.28, sine of 6.28 times t divided by 10. So let's take a look at that. We'll run this over 50 frames, and we can see, okay, so over every 10 frames, it's doing a full oscillation up to 10, back through 0, down to -10. So you can see we're already getting a tremendous range of possible things. We have my version, E1, which is giving us a small oscillation over much longer period of frames. And then we have the default that comes with the notebook that's giving us a much larger oscillation much more quickly. So let's take a look at some other options here. First of all, we may not always want to pass our values through 0. I'm going to go back and just look at 50 frames here. So I could, for instance, just add a fixed value at the end of this and say, I'll add it to mine and change mine, make it quicker, and I'll just add 1 to it. So now we see mine has all been raised above the blue 0 line. So you can see mine is still not going very high, it's only going to 1, so I can make it larger. But the important thing here is that if I'm going to multiply it now, I can't do the same thing. I can't just say 5 times sine 2 pi t divided by 20 plus 1. I have to multiply the result. So it's 5 times the previous result, which is already shifted above 0. And now I'll get a large positive. This orange one is my new one, right? It starts at 5, goes up to 10, drops back through 5, ends at 0, and repeats. So you can play with this to get different movement. And the nice thing also about trigonometric functions is this is how circles and ovals are made. So yes, it's moving back and forth in an oscillation, but in combination with a cosine, a sine and a cosine together can give you a circular movement or an elliptical movement or a Lissajous movement. And all of those are pretty interesting. So let's say, for instance, that we want, I'll just match all the values, except I'm going to make 1 cosine and 1 sine. And I'm going to drop the plus 1 and let them go around 0. So I've got 5 times sine and 5 times cosine, matching all the values, and evaluate the expression. And see, I've got 2 out-of-phase waves. One's a sine and one's a cosine. And if I assign 1 to x and 1 to z, now my camera will be moving in a circle. Now this is a little hard to visualize when you look at it this way, so let's take a look at it over here. Sine, I have sine and cosine, and there's them moving up and down, out of phase, like we just saw. But if you combine them, their final movement is circular. And the nice thing is, as soon as you start to do some math on them, you get ovals and you get overlapping patterns. So the ovals would be, if I do two times sine t, and my Lissajous are going to be if I multiply t itself. So now you can get some very complicated and interesting patterns just by combining different multiplications. And the rule of thumb to remember is that if you multiply the result, you're creating ovals. But if you multiply t, you're creating patterns. Multiplying t is changing the frequency, whereas multiplying the result is changing the amplitude. And of course, if I want the dots to be moving in that pattern too, I need to match it here. And this is a great site, Desmos. You can go in here and try it out. And the reason why we're doing both Desmos and the command line is that the command line allows us to use exactly the same format that we're going to use in the notebook. Whereas in Desmos, it's close, but it's a little bit dissimilar. And so you're not actually troubleshooting your expression while testing it. So let's take a look at a few more possibilities here. Another thing that we can do is we can use greater than, less than, and equal. So let's copy this expression here, make it expression 3, and we'll say all the same, except we're going to multiply it by whether or not it's greater than 0. So if it's greater than 0, the result of this side will be 1. And if it's less than 0, the result of this side will be 0, which means it's going to chop off all the negative values and set them to 0. So let's take a look at what that looks like. Right, so it's just giving us the top half. So some parameter could stay flat and then rise up, come down, stay flat for a while, rise up, come down, stay flat. So that's a nice possibility. And the other thing that this also gives us, this greater than, just also gives us a square wave. If we use this half of the expression alone, we just say when this expression is greater than 0, call this E4, take a look at what E4 gives us. It just gives us 1, 0, 1, 0, 1, 0. And of course, we can multiply that by whatever value we want. 10 times this expression gives us 10, 0, 10, 0, 10, 0. So that's a nice way to create alternating values. And I'm doing this with the cosine, but if I do it with the sine, we'll see that it lines up with the orange sine. When the orange sine wave is greater than 0, this value jumps up to 10 because we've multiplied it by 10. Change that to the sine. And we can look at E3 and E4 together like so. Oh, I've got a sine. Well, that's interesting. I've got a sine and a cosine, and now I've got a new shape. I meant to change both of these to sine, but you see, once you can visualize what's happening, you start just creating interesting shapes and patterns by play. Whereas it's very, very hard to intuit if you can't visualize the graph. So this is what I intended to do. So E3 is giving me only the sine wave when it's greater than 0. And E4 is giving me the truth of whether it's greater than 0. 1 being the value for true multiplied by 10. So what else can we do? We've also got the ability to chop off the decimal points and deal with integers, which will give us stepped sequences. So we can do something like floor of our oscillating value times 3. And floor, let's just look at E5 by itself. So floor just chops off the decimal portion of a floating point number, or to think of it another way, it rounds down. So here we're getting values, let's make this 5. So I get 0, and then it is going to jump to 1, and then jump to 2, and then jump to 3, and then jump to 4 by frame 10. So it's gonna stay on a value and then quickly move to the next value. And it's a little bit hard to see on this chart. It probably would be easier to see with a greater number of frames. Yeah, here you can get a better sense of what's actually happening. It's stair-stepping from value to value. Another thing that we talked about earlier that we haven't looked at yet is the modulo. And the modulo is going to give us that sawtooth pattern. We can just say, for instance, T mod 5, that's just going to give us a sawtooth. Every 5 frames it's going to drop back down. And this of course can be whatever number we want. If we want a ramp that goes up for 25 frames and then drops down, we can get that. So the value is going to increase for 25 frames, then drop. Increase for 25 frames. And if we wanted to increase to some lesser value, we could just take this and say divide by 10, and now it's the same shape, but it's increasing to 2.5, dropping down 2.5 instead of 25. And then we can change the shape of things a bit. We can change the curve of things. For instance, one way to do that is to square them or cube them. So we'll say, just take this exact thing and square the result, which in this library is double star 2. So let's change over to look at our E8 squared. Here's the shape of it to the 4th power. We can also combine that with sine. So let's go back up to E1 here, copy it, and we'll make it E9. And we'll take out the 5 times. We'll just say our basic sine function cubed and run that. And I've added a space there, which I'm not allowed to do. There we go. And so this is our sine function cubed. Let's compare that against our original sine function, E1. And we'll remove the times 5 from that. We can see green is our original sine function, and orange is our sine function cubed, or to the 4th power, or to the 5th power, or to the 6th power. And notice on the even powers it gives us only positive values, which leads me to one more thing. I'll just cover one more thing here, which is absolute values. So here's E10. Take a look at E10 here. And if I just do the ABS, the absolute value, it's just going to take negative numbers and turn them positive, which gives us this nice lumpy shape. And you can use these in any combination. I can now take this and square it. So you've got a tremendous amount of flexibility for controlling the way things move. And if you want to use this in combination with Desmos so you can see it in action, I think it gives you a powerful tool for working out your formulas and visualizing them before you commit to the time of doing a run with them. So I hope that's useful to you. Hit me up with any questions.